Hello, welcome to today's class. Today I want us to look at the concept of radioactivity. Now, radioactivity simply tells us that there are certain materials on their own they split, because the reason why they split is because their nucleus are always unstable, so they split in order to achieve stability. So as they split, they disintegrate into parts, and then they emit certain ionizing particles, and those particles are alpha particles, beta particles, and we have gamma rays or gamma radiation. Now, because of this, we can now, having discussed these two things, the particles that are emitted and the nucleus. So the nucleus, for radioactivity to take place, ordinarily, the nucleus of that atom must be unstable. So if the nucleus of the atom is unstable, then it will split. But if the nucleus of the atom is stable, then it will not disintegrate on its own unless it is made to disintegrate by man. Of course, that is artificial radioactivity. So let us now define radioactivity. Now, by definition, we can say that radioactivity is nothing but a spontaneous decay or disintegration of unstable nucleus, during which alpha particles, beta particles, or gamma rays, or a combination of these three, are emitted and release of a huge amount of energy. So during radioactivity, either of these particles are emitted, or a combination of these three. It can be two, it can be one. And then during that emission is accompanied by release of energy. Now, this radioactivity is always produced or is occurred as a result of unstable nucleus. Now, the first clue to the study of radioactivity was given by a French scientist called Henry Becquerel. In 1896. Now, this Henry Becquerel, in his studies, he discovered that yes, there are particles, there are some elements on their own. They split, they disintegrate, they decay into other smaller elements just to achieve stability, and they release these particles. So this man, Henry Becquerel, gave the first clue to this study of these subatomic particles and the study of these radioactive elements. Of course, in his own, he observed that yes, uranium was splitting into different fragments, emitting these particles, these subatomic particles. Now, he gave the first clue. Now, from that, other scientists like Maria Curie also observed that there are some other materials, some other elements, which are called radioactive elements. Radioactive elements. Or they can be called radioactive salts. Those salts, radioactive salts, are those salts or those elements that on their own they undergo radioactive decay on their own. They split in different parts and then emit ionizing radiation such as this and release of energy. So because of that, this man and not the others gave insight of what radioactivity is all about and the study of these subatomic particles. Now, let us look at some other materials. Now, from what Henry Becquerel discovered, he discovered that uranium was more active. So those uranium was emitting radiation. So he placed this uranium in a lead block, and then left. This is a uranium salt. He placed it in a lead block and then left an opening. So from there, radiations were coming out. Radiations were coming out. Now, seeing this, he observed 3 different radiations coming up here. So this is uranium salts, and this is a lead block. So when these radiations were coming up, he said, okay, since they are coming up, what do we do? He now subjected them into magnetic field. So when he subjected these into magnetic field, and of course here is a south pole and here is north pole. Now these radiations, this one deflected like this, and then this other one gave a deflection, and then this one, which is the middle, passed on undeflected. Now because of this, he now called these alpha particle and then called these beta particle. Now because of course there is a strong deflection here, strong or much deflection. Now this one, there is slight deflection. Now this deflection is as a result of what to call, from the intermolecular force of attraction, is repulsion. Now he subjected them into electric field. So this is a magnetic field, and he observed this. So when he now subjected them into electric field, and of course here is negative, and then here is positive. Now because alpha particle is because alpha particle possess positive charge, because of this there is repulsion. Both it is deflecting towards this, or it's repelled towards this direction. Now this other one too, because this one possesses negative charge, because of this negative charge here, it now deflects to the right, and because of that, he now called this beta particle. And then called this one that is deflected, slightly deflected, he called it alpha particle. Now, this is the first clue on what these subatomic particles are. Now, because there is a slight deflection to this side and there is much deflection. Now, he also, of course, most questions, most exam questions, we can as well say this, and we can represent both the magnetic field and that of electric field. So for magnet, of course, the poles of a magnet is the south and the north. Now watch this. Towards the south, the alpha particle deflected towards the south, while the beta particle deflected towards the north. And on this north one is something as this positive polarity, and this is a negative polarity. Now there are other elements too, or those radioactive sources that can still exhibit this character, such as, so we said those radioactive elements, radioactive elements are, we have polonium. Polonium is a radioactive element. We have cesium. Cesium is a radioactive element. We also have thorium. Thorium is a radioactive element. We have radon. We have radium. All these are radioactive elements. They can act the same way uranium acted here. Now we can now look at these types of radiation. These types of radiation we have. So sorry, this one that is left undeflected here is called gamma ray. This gamma ray has no charge. this one has a positive, this one has a negative charge, which is the beta particle, and the alpha particle has a positive charge. Of radiations, types of radiations. Now, there are basically three types of radiation, just as we just discussed. One, we have the alpha particle. Two, we have the beta particle. And the third one is the gamma ray. Now, let us take them one after the other. Alpha particle. An alpha particle is nothing but a positively charged high energy particle that is released from the nucleus of an atom during radioactive decay. No, so with this we say it is positively charged and high energy. So it is called, this alpha particle is a helium nucleus. So it is a helium. It is a helium nucleus represented with the chemical symbol H42. Now, what it means is that if an element emits an alpha particle, so that means it emits a helium nucleus. Of course, there are scenarios where during radioactive decay, an element can emit either 2 or 3 alpha particles or 4 alpha particles. So in that case, you still represent it. So what it means is that if an element emits an alpha particle, the mass number, which this one is 4, while the atomic number here is 2. That means the new element, which is called the daughter nucleus, its mass number will be reduced by 4, and its atomic number will be reduced by 2. For example, assuming I have an element X with atomic number, maybe we can have atomic number Z and mass number A. Now, it means that if it is undergoing radioactivity, let's say it's decayed into a daughter nucleus, Y. This is a parent nuclei now. This is a daughter nuclei plus 1 alpha particle, an alpha particle which is 4 here and 2 here, plus energy released. So in other words, the mass number of this one will be reduced by 4. That means we have here we have A minus 4. While the atomic number will be reduced by 2, we'll now have Z minus, this is Z minus 2. Z minus 2 plus this. So this is a representation of a situation whereby an element X releases just a single alpha particle plus the energy. So this one is a parent nuclei, while this is a daughter nuclei. Remember, this one is still radioactive. It can split or it can disintegrate or decay into another element. Now, the next one we have, the second type of radiation we have here is the beta particle. A beta particle is high energy positive electron produced during the radioactive decay. Alright, in this case, we say that a beta particle is an electron. It's an electron represented by the symbol 0e as electron. We have 0 there, and then we have minus 1 here. For this case, we can still have a scenario where we have electron here 0 and then plus 1. These are two different things. This one is called a positron. Of course, it is a positive electron, while this one is electron. Of course, it is a negative electron. Now, by implication, if an element releases, for example, a negative electron, what it means that here we will now take another. This is the first one. The second one, which is for this, if an element X, A here, Z here, this is the mass number, this is the atomic number. If it releases, let's say it emits just one electron to have its daughter element, let's say its daughter nuclei, let us represent it with K, plus one electron, 0 here, minus 1 here, plus energy. That energy can be here. Now, in other words, this new element that is released, or called the daughter element, the mass number, because here is 0, the mass number will be unchanged. Nothing will happen to the mass number. So we return the mass number as A. While the atomic number, because of this negative now, will increase by 1. Remember, this one is positive. This one reduced by 2. But because of this negative here, it will now reduce by 1. So in other words, here when I have Z plus 1 here, they are not the same thing. They are not the same thing with this, please. These two things are not the same. So anytime an element emits one electron or either one electron or one beta particle or more than one. So if it is more than one, that means here will be 2. And if it is 2, it means that the proton number or the atomic mass of this one will now be increased by 2. That is what this implies. Okay. Now, the difference between alpha particle and a beta particle as a product of radioactive decay is that for alpha particle, the charge of an alpha particle, charge of alpha particle is, the charge of an alpha particle is plus 2 electron, 2 times positive 2 times electron, while the charge of a beta particle is just 1 electron, just 1 electron. That means the charge of an alpha particle is times 2 of that of an electron. Take note of that. Another thing to note is that yes, the mass now, this one is more massive. The alpha particle is more massive than the beta particle. Okay. In terms of penetration, beta particle penetrates more than alpha particle. An alpha particle can, a sheet of paper cannot stop an alpha particle, but a sheet of paper cannot stop this one. Even wood, this one can penetrate through wood. It can penetrate through iron. So the only thing that can stop this is aluminum foil, that can, or gold foil can stop a beta particle, whereas an alpha particle can be stopped by ordinary paper, or even cloth can stop this one. But this one, alpha particle, is more harmful than a beta particle. Now, the third type of particle or radiation is the gamma ray. And of course, because gamma is not during that the initial explanation, gamma was emitted undeflected. So even both the electric field and the magnetic field have no effect on this. Because of that, we call this radiation. This is just an electromagnetic radiation of very short wavelength. Now, of all these three, this one has the shortest wavelength. Alpha particle has the longest wavelength. Now, this one has more penetration power than the alpha particle. So, of all these three, gamma ray has more penetrating power than both alpha particle and beta particle. Now, gamma ray can be represented by this chemical symbol. Gamma ray can be represented by the chemical symbol gamma. 0 here, 0 here. So in other words, if an element emits an alpha, if an element emits a gamma ray, even if it's 1 million gamma rays, both the mass number and the atomic number will be on of the new element will be unchanged, because here is 0, here is 0. It does not have both. This one will not have any effect on the mass number of the new element. Neither will the proton number or the atomic number have if any effect on the new element. So in other words, number 3, assuming we have an element here, X, which will give us, here is the mass number A, and this is the atomic number Z. If it emits gamma radiation, assuming we have this our Z, this Z is the new element plus the gamma radiation plus the energy. If you have these 3 things, the new element will still maintain, here is 0, here is 0. That means this one will still maintain its A, and this one will still maintain its Z. So of course these two now, if you look at these two, they are isotopes. They are isotopes. They have the same. They have the same mass number. Sorry, they are not isotopes. Please, we'll look at isotope later. They are isobars. They are two different things. They have the same mass number and then the same proton number or the atomic number. Okay, let us now look at the types of radioactivity we have. The types of radioactivity, types of radioactivity. There are basically 2 types of radioactivity. We have the natural radioactivity and we have the artificial radioactivity. So number 1, we have the natural radioactivity, and the second one we have the artificial radioactivity. Now we'll start with the first one, natural radioactivity. Now for natural, the difference between these two is that for natural radioactivity, the nucleus is unstable. That is the only difference between the two. While for artificial radioactivity, the nucleus is stable. That is the only difference between the two. Natural radioactivity, the nucleus is unstable. This one is stable. So for natural radioactivity, it is spontaneous decay or disintegration of unstable nucleus, during which those 3 ionizing radiations are produced, or a combination of any of them, alpha, beta, and gamma are produced, plus release of huge amount of energy. And because the energy is released in this, and then we cannot have certain equations. For example, we can have radium 226, let's say 86. Now if it is undergoing natural radioactivity, it can decay to radon. Radon plus 1 alpha particle plus energy released. Energy must be released. Now what it means is that the mass number of this radon, which is the product of this, is reduced by 4. And if this reduces by 4, we now have 222. And then the atomic number of this one will now be reduced by 2, which will give us 84. And that is the equation. We can also have another one where we have thorium. So if you have uranium 23892, now if it undergoes the natural radioactivity with thorium, it can now emit thorium plus, let's say, 2 alpha particles. Each 2 alpha particles will now have 4 here, 2 here, plus energy. Now, our work here now is to find out, since this one is releasing 2 alpha particles, what do we have here? So, this one is 2 times 4. 2 times 4 is 8. That means this one, the reduced new element, tutoring, we have its mass number reduced by 8. And then 238 minus 8 will give us 230. Now, the next thing now is this atomic number. This atomic number here is 2. 2 times 2, 4. Now, if you subtract 4 from 92, we will now have 88. So, this is the daughter nuclei. Remember, the nucleus of this one also is unstable. It can still split, it can still disintegrate on its own and then emit other ionizing particle. So the essence of this splitting is to achieve stability. So these are some of the examples of the artificial natural radioactivity. For the second one, which is the artificial radioactivity, for this, the nucleus is stable. Because the nucleus is stable, it doesn't have any business with splitting, disintegration, or decaying. Now, in other words, all you need to do is to cause it. So you can cause it to undergo radioactive decay manually or artificially by bombarding the nucleus of this element, bombard it with a fast-moving element. An element such as you can even use this to bombard this alpha particle. You can bombard it with an electron. You can bombard it with neutron. You can bombard it with proton or whatever you can think of. So once you bombard it, the element will absorb that fast-moving particle. With time, the nucleus will now become unstable. The moment it becomes unstable, it can now start to split into different fragments just to achieve stability. And of course, because this one is induced, you need to control it. If you don't control this, it will continue like that. And of course, if you are working in a laboratory where radiations are flying up here and there, you need to guard yourself so that this one doesn't inhale, because the exposure rate will determine the extent to which it will have effect on human health. So let us look at the artificial radioactivity. And of course, we can define artificial radioactivity as the disintegration of a stable nucleus of an atom, during which ionizing radiations are produced and release of a huge amount of energy. So, in other words, since the nucleus is stable, you bombard. So, it is nothing but the disintegration, spontaneous disintegration of stable nucleus. During that process, those ionizing radiations are produced as a result of, it is not on its own, but as a result of that bombardment. So let us look at how you can bombard elements to get them. Where you have aluminium, if you have aluminium 2735, you can bombard it with neutron. If you bombard, if you look at it as a plus here, meaning that this is bombarded with a neutron. So if it is bombarded with neutron, we can now have its new element. The new element can give us sodium plus 1 alpha particle, and then we have the energy with our energy. Now, how do we get the mass number of this sodium? We add, because this is bombarded, 1 plus 27 is 28. Now, 28 minus 4 will give us 24. Now, this one, remember here is 0. So if you add 35 to 0, it will still remain 35. 35 minus 2 will give us 33. So this is sodium. Okay. And then, sorry, this is 13, please. This is 13. 13 plus this will still give us 13 here. Sorry, 13 minus 2 will give us 11. So that is the correct one. It is 11 here. Now we can also remember at this point now, this one was initially not able to undergo radioactivity because his nucleus is stable. Now this one now is unstable now because it can undergo radioactivity on its own because of the presence of this neutron that was used to produce this. So this is a product of this because of this neutron. So it is unstable. It can now undergo radioactive decay. Assuming it undergoes radioactive decay, it becomes a parent now. So we now have sodium 2411. Instead of bombarding this again, you don't need to bombard it. It will now undergo radioactive decay on its own, giving rise to magnesium plus electron 0 and then minus 1 plus energy. So in other words, how do we get the mass number of this one? Of course, this new element, since it produced an electron or a beta particle, this one remains 24. Remember what you said earlier? Because of this minus 1 now, the mass number, the atomic number of the new element will be increased by 1. So this is 11. If you add 1 here, we'll now have 12. Still, this magnesium is stable, is on stable nucleus. It has the capacity to break again into another element and then release. It might release a neutron. It might release any other particle. Okay, we can now have, assuming we have an element as a sulfur. Sulfur is 34 here, 34 and 10 here. If you bombard it with a neutron, 1 here, 0 here, it can still give us another element. Let's say sulfur plus neutron. If it is neutron, okay, plus energy. Now in this case, it here is still 10. Here is still 10. Why the mass number will give us what? 35. If you look at this, these two are isotopes. These two are isotopes. The same element, the same atomic number, but different mass number. Okay, we can also have something like barium. Sorry, we can still have something like this. And if you have this, bromine 7935. Now you induce it with, you bombard it with neutron, and if you do that, it will still give us the same element, bromine 7. It is now going to be bromine 80, and then here is 35 plus energy. Now, looking at these two equations, bromine and sulfur, they are isotopes. Now, because of this, it will now lead us to what we call radioisotopes. Radioisotopes. And of course, isotopes are, from what we have here, isotopes are two or more elements having the same atomic number but different mass numbers. The same thing is applicable here. Now, in physics, with over 10 years marking experience, they will not ask you to define isotope in physics, no. Rather, they will ask you to define radioisotopes. So in other words, if you want to define radioisotopes, simply tell them that yes, radioisotopes are radionuclides having the same two or more radionuclides of the same element, having the same proton number or the same atomic number, but different mass numbers. So once they have different mass numbers, they are radioisotopes. And of course, there are some books also. There are some prominent books. I may not mention the name. One year, they asked in examination for students to define radioisotopes. So many of them, they were just copywriting exactly what we have in that book. Please, I want to use this medium to enlighten us. Please, some of these books need little revision. Yes, even though we arrived at radioisotope as a result of bombardment of elements with fast moving particles. So most of these books, they have it that yes, they are that radioisotopes are those materials that are arrived, those elements that are achieved by bombarding elements with fast moving particles. They may be right, but for exam purposes, please, if such question occurs, just tell them that yes, radioisotopes are radionuclides of the same elements, having the same mass number, so having the same atomic number but different mass numbers. And of course, remember, if you don't want to use mass number, you can now say, remember, this is a atomic number, which is the proton number. Here is the mass number. Mass number A is, here we have A plus N, which will give us this, or sorry, A minus mass number minus the atomic number will give us N. So this is minus the proton number, which is this. Whatever is remaining will now give us the. Therefore, if you now add neutron and proton, will give you this mass number. So you can always say that yes, they have the same proton number but different neutron numbers. It's still obtainable. So you can tell them that yes, radioisotopes are those radionuclides having the same proton number but different neutron number. You can still say that it is obtainable. Okay, now having discussed natural radioactivity and the artificial radioactivity, let us now look at some of the uses of radioactivity. Now, radioactivity has a lot of so many uses, but please, as if you are writing any exam, be careful. For example, if you say that radioactivity are used in radio dating, there is nothing like radio dating. Radio dating, no. Even though we mean that yes, it is just a process used in determining the age of a rock. If you write radio dating, you can put it semicolon and then go ahead to explain what you mean by radio dating. If you say they are using radiotherapy or radiotherapy, put it as a colon, explain what you mean by that. So in other words, let us take some of these uses of radioactivity. So one of the uses of radioactivity is that it is, of course, it has its peaceful uses. In an exam, if you are asked to state some uses or peaceful uses of radioactivity, you do not need to tell them that it is used in the production of an atomic bomb. No. So apart from that, there are other peaceful uses. So number one, we can say that yes, radioactivity is used in geophysics or in geology to estimate the age of rock or to estimate the time when an animal died, a plant or animal died. Another one, you can still tell us that yes, they are used in agriculture to determine or to determine, they are used in agriculture as preservatives or as fertilizers or tracers, or to check the distribution of fluid in plants or water in animals. So these are some of the uses. You can also tell them that yes, that radioactivity is also used in the industries to determine flaws in metal casting or welded joints. You can also tell that yes, it is used in medicine. Instead of telling us that yes, it is used in radiotherapy or radiotherapy, full stop, no. Tell us that yes, it is used in medicine for treating cancer patients. So it's a used in medicine for treatment of cancer patients and all the rest of them. So we can now go ahead to take take several calculations. We'll take the first question. This question says, a radioactive element X with atomic number 88 and mass number 226 emits in succession 1. An alpha particle, 2. Beta particle, 3. Gamma ray. So it emits in succession alpha particle, beta particle, and gamma ray. Explain using equations where necessary the changes that take place in the atomic structure of the element at each stage. Explain using equations where necessary the changes that occur in each stage. Now, solution. They said an element X has its atomic number 88 and a mass number 226. They said explain using equations where necessary the changes that occur in the new element at each stage. Because they said it emits in succession. That means after emitting this one, it emitted this and emitted this. So this is the element. So now the first question here. This is the element. Let's say this is a new element now when it emitted an alpha particle. That means this is the alpha particle here, 42 plus NH. Now, the new element, remember we said here will be reduced by 4. That means 226 minus 4 will give us a 222. And then the atomic number will now give us, if you remove 2 from here, this new one will be reduced by 2, which will give us 86. Simple. Now, they said explain. Now, the explanation can go like this. You can tell them, yes, by emission of an alpha particle, the new element Y has its mass number reduced by 2, by its mass number reduced by 4, giving us 222, and its atomic number reduced by 2, giving rise to Y with proton number or atomic number 86. What is the equation? Now, the second one, since it emits in succession, this one now will now be the parent element down. So we have 22286 here. So this one will now undergo radioactive decay. And it is now this one that will now emit this. So the new element can be, we can say Z. It can be Z plus beta particle. This beta particle is 0 and minus 1 here. So which will now give us, because this here is 0, it will not have any effect on this. We will return 222. This is minus 1. Remember we said that if it emits an electron, because of this minus 1, the new element, the mass number, the atomic number of the new element will be increased by 1. So because of that, if you add 1 here, we'll now have 87 plus NH. Okay, this is the equation. To explain it, we can now say that yes, that by the addition of a beta particle, the new element produced is Z, which has its mass number the same as this, which is 222, and has its atomic number increased by 1, giving rise to its atomic number to be 87. And that is D. Now, for the third one, since it emits in succession, it is now this one that will emit gamma ray. So we now have Z22287 here. Z will now give rise to another element. Let's say K. It can be K. You can use any letter to represent it. So if it is K plus gamma, gamma here is 0, here is 0, plus NH. Now, if it is energy, remember here is 0, here is 0. It will not have any effect on this. This and this will not give us 222. Here will return the same 87. So this is the changes that occur when this element with this as the mass number and this as the proton number emits in succession this. Okay, now we'll take the next question. Okay, so the second question goes like this. We have this equation. Remember, here is P, unknown. Here is Q, unknown. For this one, bismuth. For bismuth here, we have these two as unknown. Now here the question says, determine the values of question I. Determine the values of P and Q in equation 1, equation A. Now the values of M and N in equation B, and identify X. So this is the equation. From here, this is the question. They said determine the values of P and Q in equation 1. Then 2 is M and N in equation B. Please. This is equation B. In equation B. And identify X. What is X? Solution. If you have this type of problem, it's very easy. All you need to do is take this arrow as your equality sign. Is equal sign. This equates all the mass numbers and equates all the atomic numbers. So when I go for the first one, number 1, we have, if we equate all the mass numbers, we have 222 is equal to, this one is our equality sign, is equal to this one, 218 plus Q. Now, and of course, we have Q is equal to, we send this one here, 222 minus 218. Therefore, Q is equal to 222 minus 218. If we press your calculator, we have 4. 222 minus 218. It's Q is equal to 4. Now we have the still on this one now, equate all the proton numbers. We have P is equal to 84 plus 2, which will give us 86. Therefore, P is equal to 86. We have gotten that one. Now, for the second one, M and N, number 2, M and N, the same way, equate all these mass numbers. That means 214 is equal to 214 plus M. Therefore, M is equal to 214. Send this one here, it becomes minus 214. Therefore, M is equal to 0. Now, for the second one, equate the atomic numbers, which will give us 83 is equal to 84 plus N, which will give us 84, which will give us N is equal to, take this one here, 83 minus 84. Therefore, N is equal to minus 1. So we can now come back here to say that from here, we now say that the first question, P is equal to 86. Q is equal to 4. N is equal to minus 1. And M is equal to 0. So if we now come to this equation, since they say identify X, we can come here and put M 0 here and put N to be minus 1. And of course, it's only an alpha particle, sorry, it's only an electron or a beta particle that has 0 here and -1 here. Therefore, we can now say that X is a beta particle. It's a beta particle. Or you can say that X is an electron. So that is the answer to that one. We can also take another question, but before that, we'll clean the book. Take this example 3 that says 8 alpha particles and 6 beta particles are emitted from an atom of uranium. 23892. Are emitted from an atom of uranium 23892 before it achieves stability. What is the mass and atomic numbers of the final product in the chain reaction? What is the mass and the atomic numbers of the final product in the chain reaction? So what we are going to do here now is, remember, this is the uranium 23892. Okay. Now, it gives rise to, let's say, X. This X is, let's say, P here and Q here, plus 8 alpha particles, plus 6 beta particles. Now, plus energy. So this is the equation. Now they say what is the mass number and the atomic number of this is the final product. Now all we need to do is to explain all this, is express this. If we express that, we now have uranium 23892 giving rise to X, P, and the Q, plus 8, since this is alpha particle, 8 into helium. So this is a helium 42 plus 6 into electron 0 here and -1 here. So yes, plus energy. So in other words, we can now have this as if we expand that, we have uranium 23892 giving rise to X, P, Q, plus 8 times 4. 8 times 4 is 32. 8 times 4 is 32. That means this is helium. Helium is having 32 here. 8 times 2 is 16 here. That is what helium is having. Plus, we have 6 times 0, 0. 6 times -1 is -6 here. Plus energy. So, in other words, we can now, at this point now, this is the final point. At this point, we cannot equate all the mass numbers. We can equate the mass numbers and equate the atomic numbers. So if we equate the mass numbers, we have 238 is equal to P plus 32 plus 0, which will now give us that P is equal to, we send this one here, 238 minus 32. Therefore, P, which is the mass number, will now give us 238 minus 32, and it will give us 206. Now, if we equate the atomic numbers, 92 is equal to Q plus 16 minus 6, which will now give us 92 is equal to Q plus 10. Now, Q will give us 92 first. 92. We'll send this one here, minus 82. Minus 10, please. Minus 10. Therefore, Q is equal to 82. Therefore, you can now say that Q, which is, sorry, the new element X, P is 206. We can come here and write 206 here, and then X here we can write 82. So this is the mass and atomic number of the new element X. So we can still take another question, but not the least question. The question says, when nitrogen with mass number 14 and atomic number 7 is bombarded with neutrons, the collision result is disintegration in which alpha particles are produced. Represent the transmutation in a symbolic equation. We have here that nitrogen is being bombarded with a neutron, and then the product has alpha particle as one of the products. So they said represent it in a symbolic equation. Solution. We have, this is the nitrogen with mass number 14 and atomic number 7 is bombarded with a neutron, and of course a neutron has 1 here, 0 here. Remember, they said the product has an alpha particle in it. That means we have X plus alpha particle, 42 plus NH. Now, the equation, this is the equation, but we need to balance it, get our mass number and our proton number. So 14 plus 1 is 15. Now already we have 4 here. So 15 minus 4 will give us 11. That means here is 11 plus 4 will give us 15 on this side. And of course here is 15. On this side also we have 2 here. 7 plus 0 is 7. Already we have 2. So what we have here is 5. 5 plus 2 will give us 7. So this is the equation that will give us what we are looking for. Please, this is where we will stop the question, the topic for now. Please join me in my next lesson, where I will be bringing us the concept of half-life. So by next lesson, we're going to look at half-life. Please do not miss any of these videos. Like I said, this video will have 4 parts. Make sure you join me along in those 4 parts. So at the end of the day, we'll have detailed knowledge of it. But please, just before we leave, if you have not subscribed to this channel, please subscribe to this channel. If this lesson was helpful to you, please give it a thumbs up. Tell me in the comment section how you feel about this lesson. Sorry, it's very long, but thank you for being there with me until we make it. See you in my next video. Thank you very much.